Chapter 9, attractive forces. And we're not just talking about good chemistry here. So we are going to be building off of some previous ideas that we learned about. We had a little hiatus from thinking about too many concepts with our gases chapter. Our gases chapter, we got to do a little bit of algebra, a little bit of math. In chapter 7, we were doing almost exclusively concept questions, thinking about concepts, not really doing any math. We're going back to build some more on those ideas. So we looked at how do we put together molecules in chapter 7. And now in chapter 9, we're going to be thinking about how do molecules interact with each other. So there are intermolecular forces, forces between molecules. That we are going to learn about in this chapter. The specific interaction between molecules in coffee that taste bitter and taste receptors on the tongue is caused by intermolecular forces. These are attractive forces that exist between molecules. So these aren't within a molecule. These are, if you've got two molecules, how do those two molecules interact with each other? Intermolecular forces are essential for many physiological processes. These drive our biology and keep us alive. There are also less specific intermolecular forces that exist between all molecules and atoms. Intermolecular forces are the reason that we have liquids and solids. If there were no intermolecular forces, it would all be gas. And then we would just be doing chapter 8 for the rest of our lives. But in reality, we wouldn't exist. We'd just be a collection of gas particles. So we wouldn't be learning any of this. There are a couple different types of intermolecular forces. These are constant forces of attraction between molecules. The strength of the intermolecular forces how sticky the molecules are. That's basically what we're talking about with intermolecular forces. How sticky are they? Determines the state. It can be solid, liquid, or gas at room temperature. In terms of intermolecular forces, really strong intermolecular forces are going to result in solids at room temperature. Less strong intermolecular forces will result in liquids, and really weak intermolecular forces are going to result in gases. Our first force our default intermolecular force, I'm going to abbreviate intermolecular force, inter for I, M for molecular, and force for F. We're going to abbreviate it as IMF, not to be confused with the International Monetary Fund. The default intermolecular force, which is present in how many of the molecules and atoms? All of them. All molecules and atoms is the dispersion force. So the dispersion force shows up in all molecules and atoms, of course with some exceptions, but basically all. And it's also sometimes called the London force, also sometimes called London dispersion force. Often just called the dispersion force, though. Dispersion forces are caused by fluctuations in electron distribution. So remember, from chapter 7, we talked about a couple different models of how our electrons can behave with respect to our nucleus. So in our Bohr model, we were talking about something that looked like this. We've got our nucleus in the center, and we've got orbits where our electrons are, rotating around, orbiting the nucleus. And then we replace that with our more advanced quantum mechanical model, where we had S, P, D, and I'm not going to attempt drawing an F orbital. Orbitals, right? So we have these different shapes. And I don't know which one of these is positive and negative. Whatever. And these shapes were probability distributions. So for an S orbital, it's likely to be found, our electrons are likely to be found in that spherical shape. It doesn't say that they're going to be evenly distributed in that space. So they could both be on one side of that S orbital. We're going to be mostly thinking of S orbitals for our dispersion forces because it's easier. So in our S orbital, our electrons could both be on one side, and that would be a fluctuation in the electron distribution. They'd be there, and then they might be evenly distributed, one on the left, one on the right. Then they might both be on the right. Then they might both be up, both be down. Some infinite number of possibilities there. So it's related to the electrons since all atoms and molecules have electrons. Ions don't have electrons. All substances have dispersion forces. Some ions don't have electrons, that is. The electrons in an atom or molecule may, at any one instant, be unevenly distributed, and that's what causes the dispersion force. We'll see better pictures of this. Here they are, sort of. I was thinking of a different one. RIP old slides. So random fluctuations in the electron distribution, say, of a helium atom, causes instantaneous dipoles. Instantaneous means it exists for how long? An instant, a moment, a brief period of time, a short period of time. And dipoles, di meaning two, and poles meaning poles, like positive and negative. So it's a really, really small, instantaneous, very temporary magnet. So the dispersion force is a temporary magnet effect. It exists for part of the time. Most of the time it doesn't exist. So if we've got helium molecules, atoms, sorry, we've got helium A and helium B. It's possible that helium A, rather than having its electrons be nice and evenly distributed, let's use red instead, roughly evenly distributed around our nucleus. Instead, our electrons, of course I picked the wrong colors, our electrons instead both decide, hey, let's both be on the left side. So we've got our nucleus in the middle that's positively charged, and our electrons are goofing around and they're both on the left side. Because our electrons are both on the left side, there's more negative charge than we expect on that side, so we get this little music note looking thing, partial negative charge on the side with the electrons. And there's no electrons on the right side because this is helium. And so we get a partial positive charge. There's nothing blocking the positivity of the nucleus from shining through and brightening the day of the helium next to it. And that does this. So our electron's still over there. It's an instant later. And now in helium B, that can induce a dipole. It can cause a dipole to create or to exist on the other thing. So the nucleus of helium A is sort of acting like a pi for our electrons in the neighboring helium atom, and they do the cartoon floating over thing. And now those electrons are both on the left side. And so because helium A was being goofy, helium B is now also being goofy. And by goofy, I mean having a temporary dipole, like one does. So that's what's happening behind the dispersion force. How many things have the dispersion force? Everything has dispersion forces. So everything with electrons has dispersion forces. This is our baseline force. That's why it's our first one that we're learning. Everything can do this. As long as it has electrons, the electrons can be silly. They can be mismatched all over the electron or all over the atom. So that instantaneous dipole on a helium atom induces an instantaneous dipole on its neighbor. Induces meaning causes, forces, creates. Causes to come about in a neighboring atom. This is for one instant. So think of the shortest period of time that you can, and then make it shorter, and then make it shorter, and then make it shorter. Keep making it shorter. And then it's probably still too long, but we're close enough. That's how long these dipoles exist for. So they're there, and then they're gone, and they're gone, and they're gone, and they're gone, and they're there, and they're there, and they're gone, and they're there, and they're gone, and you get the idea, right? So it's that forever. That's dispersion forces. They are transient, meaning that they're constantly appearing and disappearing. So dispersion force dipoles are temporary. And because they're temporary, that makes them additionally weak on top of just being weak already. So they're not always magnets. Sometimes they're magnets. Probably most of the time they're not magnets. It's also probably possible that they're magnets for a moment, but they're not close enough to anything for that magnet to cause a dipole in another neighboring atom or molecule. So then they go away before they can even do anything. I can't think of a specific instance, but there's this phenomenon that happens sometimes where you're like, man, I really wish that I had a thing. Like just some random, I wish I really had a snack. I had snacks all day yesterday, and now I have no snacks, and I would really love to have a snack. Or like later you're like, oh, there's that snack that I wish that I had earlier. That's sort of dispersion forces in my brain. For some reason, my brain's thinking about that. All right, dispersion forces. What affects dispersion forces? The magnitude, the size of the dispersion force depends on a couple of things. How easily the electrons can polarize, and that depends on the size of the electron cloud. Big electron cloud comes from having more electrons. As you add electrons, you add shells of electrons, the electron cloud gets bigger. The bigger the cloud, the further those electrons are away, the easier they are to pull off. And it's also easier for them to just randomly be on one side versus the other. When you're at home, assuming that we have people that give us rules at home, when you're at home, it's easy for your guardians, your parents, the people that you live with to say, hey, you can't do that. When you're completely far away from them, when you're here at school, right, you can be a little bit silly, goofy. You can maybe break some of those rules a little bit. That's the same thing for electron clouds. When the electron clouds are far away because of a big electron cloud, it's easier for them to be goofy and hop over to one side of the electron cloud for some reason. So a larger electron cloud is more easily polarized. So more electrons equals bigger electron cloud equals stronger dispersion forces. And so we can use as a proxy for more electrons, molar mass. So molar mass, as molar mass increases, generally the number of electrons also increases. And so if we're comparing within a family of similar elements or compounds, like for example, noble gases, or for compounds, carbohydrates. Things like CH4, C2H6, C3H10, H8, stuff like that. We can compare magnitude of dispersion forces for things like these, if they're in a similar group. So let's look at noble gases. For our noble gases, here we have our noble gases listed out in the order that you find them on the periodic table, top to bottom. We've also got their molar masses, and we've got their boiling points. These are all gases at room temperature, so we're listing boiling points. Later we'll be seeing melting point perhaps as well. So for our molar mass, helium has a molar mass of 4. It's got a boiling point of 4.2, and that's in Kelvin. So that's really low. 4 Kelvin is super cold. Neon has a larger molar mass, meaning it has more electrons, and so it has a higher boiling point. It takes a little bit more energy, not very much more energy, but a little bit more energy for those atoms to stop sticking together as a liquid and separate and go their own ways as a gas. And as we increase molar mass, we can see that the boiling point also increases. As molar mass increases, boiling point increases. Stronger IMF, intermolecular forces, means higher boiling point. The opposite would also be true if we're comparing within a family of chemicals. A higher boiling point means stronger intermolecular forces. The two things are related. How easily they can separate is related to how sticky they are. If they're really sticky, they're harder to separate. That means a higher boiling point. Hydrocarbons are a class of chemical containing only carbon and hydrogen. Which hydrocarbon, C2H6 or C4H10, ethane or butane, has the higher boiling point? So we're comparing within a similar class of compounds. These have an intermolecular force that they have access to. What's that intermolecular force? Dispersion forces. Dispersion forces, as we increase molar mass, we increase the strength of dispersion forces. Which one of these two chemicals is going to have stronger dispersion forces? We're looking for higher boiling point. A higher boiling point, is that going to mean stronger or weaker dispersion forces? Stronger dispersion forces. I'm going to write the general International Monetary Fund. Sorry, intermolecular forces. I did actually screw up there. So stronger IMF intermolecular forces are dispersion forces. Which one of these two is going to have stronger intermolecular forces? C4H10 has more mass, electrons, so it has stronger dispersion forces. And we will learn about some of our other intermolecular forces next class.